Today I'll talk about hard rods and integrability braking traps. This work is done with Debarshi, Professor Abhishek, Professor Manas, Professor Anupam, Veer, and Professor David. So classical integrable systems are systems which have infinitely many conservation laws, and these, conserve quantities, and these conserved quantities are in involution with each other, in the sense they are independent. But realistic systems, it's easy to break this integrability in a sense that even a small imperfection or defect will break. So a natural question arises, what is the effect of this integrability breaking? So this has been studied for many problems, many phenomena, like what happens in transport, where TODA model, which is a integrable model, confined, when a pinning potential is added, what happens is the transport properties change from ballistic to diffusive when the temperature is increased, when harmonic pinning is present. And for a quartic trap pinning, it's actually diffusive. In a similar ergodicity properties have also been studied, where harmonic chain, which is a integrable model but a non-ergodic model, when an harmonic term is added to the system, it becomes chaotic and ergodic. Even the thermalization properties have been studied, and what this experiment has done is they took delta Bose gas, created an initial condition which has two density blobs, and let them evolve in an anharmonic trap. And what they see is that after thousands of collisions, these particles, these density blobs just keep oscillating back and forth, and this is something like a Newton's cradle, because there are two density blobs which go back and forth. So they say this is a quantum neutral cradle, and this does not thermalize. Does not thermalize. Something which I forgot to mention was this Bose gas itself is an integrable model without the trapping, but with trapping the integrability is broken. So even a classical problem has been studied, where hard rods and harmonic traps have been studied, where they see that it eventually goes to a stationary state, but this is different from the Gibbs stationary state or a Gibbs equilibrium. And in this work, they had looked at energies which were smaller, or small temperatures. We were interested in looking at higher temperatures also, and the effect of an harmonic trap. So that's what we do. So the model we have is a bunch of hard rods which are integrable. They are integrable because when two hard rods collide, they collide elastically and they exchange momenta. So the amount of momentas, the configuration is changing, but the momentas are all conserved. And we confine them in a harmonic and quartic trap separately, and we want to understand whether it thermalizes or not. But to understand whether it's thermalized, we need to understand how the equilibrium looks like. So that's the first thing we do, and then we study whether these are chaotic and ergodic systems, and then we eventually ask the question whether they thermalize to the Gibbs state. So to start with the free energy, we want to find the equilibrium density profile, let's say. So we have to start with partition function. To compute the partition function, we have to know first of all what is the ensemble we are in, but that's difficult because we don't know what are the conservation laws which are broken. So we assume that it's only energy which is conserved. So our partition function is nothing but an integral over e to the power minus beta h. So we have to do that, solve that partition function, but it's still difficult because there is this geometric constraint, the particles can't cross each other. So to take care of that, what we have done is, instead of solving the partition function for the whole system, we divide the system into smaller subsystem, and since these interactions are short range, the partition function can be written as product of partition function of smaller subsystems. And within the subsystem, we assume that the size of the subsystem is such that, and the temperature is high enough such that the particle actually does not experience the whole curvature, but it experiences almost a flat kind of potential. For a flat homogeneous potentials, we can compute how the partition function looks like. So that's what we exactly do, and find the free energy. This is an approximate method. and what we see is that the free energy has two components. One is the energy because of the trap, and there is a entropy because of the confinement and because of this constraint of non-crossing and non-overlap, and for each and there are total rho times delta x number of particles in a small subsystem. So the free energy of the whole subsystem is the sum of all the free energies of all the subsystems. Now we want to find what is the equilibrium density profile. To find that, we minimize the free energy with respect to density, and with a normalization constraint that the density is normalized to n, and we get the chemical potential equation. This equation has actually been exactly found by Perkus. So we have a same equation. Now we want to understand how the density profile looks like, but there is an explicit system size dependence inside the density profile. So to extract that n dependence to bring it out, what we have done is to work in rescaled variables, where the rescaling is given by x by n, in a sense that if you put a lot of particles in a confinement, the extent of the box, the extent of the gas will be of order n. So if you rescale the system by n, the position by n, we are in this rescaled variable, and what we find is that in this rescaled variable, the important factor is the rescaled temperature, not the original temperature, and the rescaled temperature is T by n to the power gamma, where gamma equals to 2 for harmonic and gamma equals to 4 for quartic trap. And we verify whether this analytical solution is correct or not. Of course, we can't solve this transcendental equation analytically except some asymptotics at high and low temperatures, but we do we solve it numerically and see whether it matches with our Monte Carlo simulations or not. Here you can see in harmonic and quartic trap, we have plotted the scale density profiles, and we see a very decent match between the density profile from Monte Carlo and theory. So now we understand how the equilibrium should look like. We now want to ask the question, what exactly is happening, whether this system is going to that equilibrium or not. So to start with, we have this confining trap with some spring constant, some strength, but now we want to work in variables which are independent of the rod length and spring constant, trap strength. So we just rescale the variables in this fashion. And then another thing is, this ground state energy itself is quite huge. It's not extensive, it's super extensive, because when you add particles, the particles will be added at the edges, and at edge the energy of the particle is n to the power delta. So there are n such particles, so the total energy is n to the power delta plus 1. So these are huge energies. So what we see is that the relevant parameter for further analysis is the rescaled energy and the system size n. Interestingly, for harmonic confinement, there is one conservation law which is not broken, at least that we know of. That is the center of mass energy. But for quartic confinement, it's broken. So for further analysis, we have to be careful with the center of mass energy. So we fix it to be 0. And now we have a basic setup. We have rods of length 1 in a trap strength 1 confinement, and then we want to study their dynamics. We do a molecular dynamics simulation and study the chaos, ergodicity, and thermalization properties. So let's start with what happens to 3 particles. How do we study chaos? Chaos is studied through Lyapunov exponent, the maximum Lyapunov exponent, and what we see is the maximum Lyapunov exponent for harmonic confinement as it's in a 1D trap.
So it's only the translate.
It's just going to do this and collide.
But even if they are in the chain, one can think of can take
additional degrees of freedom. We did not think of that. This is isolated system also, yeah. So what we find is what we find is the Lyapunov exponent for harmonic trap behaves very similar to log t by t. So in the large t limit, this is going to behave like, is going to 0 in a sense that it's sort of integrable like. But for the quartic trap for 3 system sizes and different epsilons, epsilon is the initial distance between the trajectories, initial conditions, we see that the Lyapunov is positive. So this suggests that, okay, this is going to be chaotic. Fine. This is going to be, could be integrable. So we just looked at the Poincare sections to confirm this. And what we look at is, we start with multiple initial conditions on a randomly chosen, and we evolve these systems, and we draw the Poincare section for different initial trajectories, initial conditions. And what we see is very regular orbits, but within this regular orbit there are some fractal structure which I've just zoomed in here. We don't understand why this fractal structure arises. This has been observed by Veer Vilchandani's work also, previous work, but we conclude that this is going to be integrable. But we don't know what is the third conservation law, because N is 3, we know 2 conservation law, third conservation law is still not known. We want to understand that, but we don't know. And for quartic confinement, as you can see, for different initial condition, different colors represent different initial conditions. You can see it's a very density profile, so it's again chaotic. Now we look at slightly larger system size, let's say n equals to 4. What we see is that Lyapunov exponent has a very strong initial condition dependence, and that dependence can also be seen in the time average temperature of the first particle, where you see different colors represent different initial conditions, and that this initial condition dependence actually persists in the larger system size also, and as you can see in the temperature profiles also. So from here what we are concluding is that because Lyapunov exponent is an initial condition dependent quantity, the system is chaotic, however not ergodic. So like we are worried, slightly worried, thermalization hoga nahi hoga. But in the quartic case, it's going to be chaotic. We find that it's chaotic and ergodic, we are safe. We also study what exactly happens to the Lyapunov exponent with increasing temperature, rescaled temperatures. What we see is that for harmonic trapping, the Lyapunov exponent decreases with increasing temperature, which is a bit counterintuitive, I guess. But this has been observed for some other models, soft rods in harmonic confinement. However, for quartic trapping, the Lyapunov exponent is increasing with increasing temperature. We are good there, and this the behavior is square root t like, and this has been conjectured for some other class of models to be square root t, but we also find this, so that has to be understood. But to understand why this is decreasing, we also looked at how many collisions are happening on an average per unit time, and there we see that the number of collision decreases with increasing temperature, increasing rescaled temperature. And in this case, the number of collisions are increasing with the rescaled temperature. This can be understood in a sense that because we increase temperature, the gas expands. If the gas expands, there is more gap the particles have to travel to collide. So in a sense, it's going to take longer, and each particle will have the same period. However, in a quartic trap, since higher energies are there, it will have smaller time scales, and this collision can happen faster at higher energies. It's a hand waving argument, but yeah. Now that we understand this, these systems are chaotic, probably not ergodic in a harmonic trap, but ergodic in quartic trap, we also want to understand what happens to the system, whether whether it's going to thermalize or not. So we start with a 2 density, the Newton's cradle kind of initial condition, where we have 2 density blobs and let them evolve. What we see is that with increasing, as it evolves for lower temperature, it's actually mixing in. This is the phase plot of one particle phase plot, rho density, one particle density plot. Here we see that these 2 blobs are actually interacting and then mixing is happening. But for lower temperature, higher temperature, we see that this mixing is slow, which is consistent with the plot which we have shown here. The Lyapunov exponent is smaller at higher temperature. Now we want to understand, okay, this is going to mix, fine. So it looks like it probably go to the steady state. But now the question is, what is this steady state going to be? So we just plot these densities, density profiles, and the velocity distributions at different times. T equals to 0 is the initial density profile. Then we look at intermediate times and a very long time. What we see is that it actually goes to a steady state. That steady state is very different from the Monte Carlo simulation. Monte Carlo simulation is our analytical expectation for the quartic case, and similarly velocity distribution also does not go to the Maxwellian e to the power minus p square by 2m. It goes to a different distribution. Yeah, so we do not understand why this is happening. However, for the quartic case, what we see is that if we start with not these initial conditions have higher energy, so difficult to compute Monte Carlo, doing molecular dynamic simulations. What we do is a flat density profile with a squeezed energy, initial energy, and we see that it actually thermalizes to, the density thermalizes to the expectation, and the velocity distribution goes to the Maxwellian distribution. So in conclusion, what we have done is we have an equilibrium description where we have find that there are only relevant parameter is the rescale temperature. And using that we have studied whether the system is going to be chaotic or not. In particular, what we found is a system with 3 system sizes in harmonic confinement are non-chaotic and non-ergodic. However, for chaotic confinement, it is chaotic and ergodic. We do not know what steady state this is going to go, and n equals to 3 also we expect it to go to equilibrium, but we haven't checked it. For 4 and larger system sizes, even though it's chaotic, we find that in harmonic confinement the system is non-ergodic. But in the larger system sizes, maybe we expect it to, we don't have a clear indication, but we hope it goes to ergodic. So it's not very clear. We are still checking it carefully, but it definitely does not go to a Gibbsian, Gibbs equilibrium state. In chaotic trap, it's fine. It's behaving chaotic, it's ergodic, it goes to a Gibbs equilibrium state. And future, what we want to do next is we want to understand this question from a hydrodynamic point of view instead of a generalized hydrodynamic point of view. Yeah, that's a future thing which we are going to do. Thank you.
Thanks, Jiten. Questions, comments?
Yeah. In the context of looking at such chaotic systems, how crucial is the number of the particles?
Yeah,
because is there a threshold where you would actually see the transition, or
yeah, we are trying to figure that out. That's a good question, because at smaller system sizes there are these CAM orbits which do not let the system thermalize, but maybe at larger system sizes they disappear. So is there a critical number? We are trying to work on it. This is a work in progress.
If I may ask one small question, in the context of Newton cradle kind of a situation, the momentum transfer generally from the initial position down all the way to the end particle is also very sensitive to the phase what you actually match between these individual elements. Okay. Given that these rods are not in physical contact with each other, if I understand correctly?
No, they do have physical contact.
Okay. So then the length of the rod becomes very important compared to the potential.
Yeah, so that's why we work in a rescale units, and any rod length can be
can be matched.
At least in a classical system. I'm not sure about the quantum situation. Yeah.
Okay. Thanks.
So, but in this context, as you are not taking care of the rotation, is the rod and or a disc will have any difference?
So since it's 1D, right? So these are colliding like this.
But there is no difference in principle.
Yeah, probably. I don't think, because we haven't considered these.
Yeah. So once you start to consider rotation, then the rod will become rod, and the sphere or the sphere, hard sphere will not be rod.
But it won't be an integrable model in the very first place, right?
But hard sphere on a line, it is integrable, right?
Which is sphere in a line with a rod.
The same thing. Yeah. So, but
In higher dimension, it's not.
but then
integrable.
why you are systematically calling rod here? So is there, while doing let's say the dynamics, is the collision different or still a contact?
It's the same thing. It's a contact. It's a contact.
It's 1D. It's nothing.
Yeah, we have a very simple integral models in 1D. Yeah.
Okay.